Calculator exercise. Slam those in. I wonder if you guys notice anything. Cosine of 40. 0.766. So what? Just a number. Cosine of 140. Interesting. Negative 0.766. Did you guys get the same numerical value for those four? It's just their signs were different depending on the CAST rule. Interesting that those numbers were all, the decimals, the numbers themselves were all equivalent. I wonder how those four angles are related to each other. Who can say? .423. 0.423. Hey, wait a sec. Did you guys get 0.423 for all these? Except the signs were different according to the CAST rule. Interesting. I wonder how those four are related to each other. And did you guys get 5.671 for all those? It just, the signs were different depending on where they were according to the CAST rule. So clearly something is going on. Clearly each set of four angles are related to each other. Can you guys have a little team talk? And can you find out what makes them all related to each other? What do they have in common? I'm going to pause my recording while you guys discuss. I'm just going to sit here and do nothing while you guys talk about that. Here's a little visual hint for how the first set of four could be related. There's one angle of that set of four in each quadrant. Maybe visualizing it like that, you can see how they're related. I'll wait a second more. Each of those angles is 40 degrees from the x-axis. 140 is 40 less than 180, while 220 is 40 more. And 320 is 40 less than 360. They all make the same angle with the x-axis. And because of all the symmetry going on here, when you look at their points on the unit circle, they're going to have similar numerical values, but their signs will be different depending on the quadrant they're in. Does this rule work with another pair? Let's just diagram out one more pair. I'm going to use my straight line tool because I have that luxury. Also, my fine motor skills are declining as I age, so there's that too. What are our four angles? 25, 55, 25. We'll draw a little X-wing here. Star Wars reference. So what do we got? We got 25. See, I don't even need to go back and look. It's 25, 155. It was 205 and 335? Question mark. But all these angles have that same thing happening. they all make a 25-degree angle with the x-axis. So this is the meat and potatoes for today, the big idea for today. These angles are all related angles, hence the title of the note. So what makes things related angles? This is the 30 seconds where you want to dial in today. What makes these angles all related to each other? Because they all have the same reference angle. We sometimes refer this as a related acute angle. It's the angle. Forrest, you listening? Sam? This is the angle that our angles of standard position make with the x-axis. So reference angle, related acute angle. The symbol we use is theta with a little subscript r. So you're going to see me tossing around. When I have a little r on the bottom, I'm referring to that related acute angle. So this reference angle is the angle made with the x-axis. And I might just put in brackets there, the acute angle made with the x-axis. See the above visual for what we mean. In each of those examples, in the first one, the reference angle was 40. All of those angles have a reference angle of 40, or a related acute angle. Doesn't exactly roll off the tongue. For the second, all four of those had a reference angle of 25 degrees. The key idea is this. Big idea for today. Related angles. I think I have too much space for this, but that's okay. Related angles have the same reference angle. Same theta r, same angle with the x-axis. However you want to slice it, that makes them related. So all of their cosines, their sines, and their tans are all going to be identical, except their signs will be different depending on the cast rule. So for these, we're going to do a little exercise, just finding some reference angles, and then seeing how things line up with the cast rule. So let's do this first one together. 163, where is that? So at this point, you guys should be comfortable with where 163 is. 163 is between 90 and 180, and it's probably a bit closer to 180. So we'll try to keep things as accurate as we can. You can get out your calculators. You can do the mental math. Has anybody figured out what the reference angle for 163 is? Colette, what's the reference angle?
17 degrees.
It's 17 degrees. How did you get 17 degrees?
180
minus 163. So you're either using mental math or just grabbing your calculator, but it's basically how much farther to go from 163 do you have to go to 180? It's 17 degrees. Up here, you can just show that calculation if you'd like. 180 minus 163. Not necessary, though. You guys are all smart individuals. Yes, Kirby. Okay. So what that means, guys, is that when you do the sine, cosine, and tan of 163, you should get the exact same numbers, not signs, but numbers as sine 17, cosine 17, and tan 17. So this is just a little verification. This isn't any new tech here. It's just seeing if this checks out. Do we get the same sine, cos, and tan numbers anyway? Remember, for 17, that's in quadrant 1. Everything should be positive. For 163, we're in that sine quadrant. So as you're calculating, just think, okay, my sine should be positive and all the rest should be negative. Does that check out here? Sine 163. Sine 163 is 0.2. We'll just go to 3 decimal places. That's fine. I'm willing to put it all on the line here. I'm not even going to put in my calculator. The sine of 17 will be 0.292 approximately. I just know it. Maybe I will double check. Yes, of course it worked. I knew it. I never had any doubts. Cosine of 163. I'm expecting that to be negative. I don't really care what the number is, but it should be negative. Cosine 163. Negative 0.956. I'm willing to bet cosine 17 is positive 0.956 because they're related and the sign should be according to the Cast rule. Did you guys get that too? All right, let's finish this one off. And we'll do a few more of those little exercises together. The tan of 163 is a thing, and it's minus 0.306. Minus, because only sine is positive in that quadrant. The tan of 17 should be the exact same number, but positive. It all fits together. They're related angles. Why are they related? Same reference angle. How you guys doing? We doing okay? So we know what a reference angle is, and we're learning how to calculate it. And we know related angles have the same reference angle. So all their ratios are identical. Their signs are different. Can you guys do this one? So I think are we doing 3 more? We're doing 4 more. Fourth one has a twist. I have not taught you guys about negative angles yet. You're going to wait for me. But you guys can do the next 2 as an exercise. Draw 240. Where is it? Find the reference angle. And then just verify the sine, cos, and tan. Numbers should match perfectly. Signs should be according to the Cast rule. When you guys get 1 or 2 of these on your unit test, whenever that is, it's like free marks. Just little verifications. 240. 240 is down here. $240 is here. The reference angle is not 30 degrees. I'm willing to bet a few of you guys have 30 degrees. It's not 30 degrees. I think I heard it. It's 60 because the reference angle is always the angle we make with the x-axis. So here, 240 is 60 more than 180. So if you wanted the calculation here, it would be 240 minus 180. 60 degrees. That means that the sine, cos, and tan of 240 and 60 should all have the exact same decimal values. Their signs should be different according to the Cast rule. And then you guys can do 342. Is 342 a little bit of overkill, perhaps? But I'd rather do a 1 more than 1 less. Timing-wise, we're doing pretty good. You guys are doing good today. Sine 240. Negative 0.866. Cosine 240 would be negative 0.5. Tan 240. 1.732. Only tan was positive, which makes sense. We're in that tan quadrant according to the Cast rule, right? Made sense that sine and cosine were negative. And we should see the exact same numbers, but all positive for cosine, sine, and tan. If it didn't work out that way, then you messed up because this works all the time. All right, 342 is in that final quadrant, and then I will talk about negative angles with you guys. 342. Where's 342? Well, that's 270. 360. Okay, so we're in between. Maybe around here. And most of you guys are just going to, after kind of drawing it out, you might not even have had to draw it out to visualize the reference angle. Somebody who hasn't helped out yet today, what's our reference angle in this case? Jaden, 18 degrees, because we're 18 shy of 360. Of course, if you weren't sure with the mental math, you would just see how far away you are. And you guys are doing great. Humor me and just verify for yourselves that these angles are related, and verify this idea that their sine, cos, and tan have the exact same numerical values. Their signs will be different according to the cast rule. Negative 0.309. Cosine should be positive, and it is. 5.1. Tan should be positive. Excuse me, tan should be negative, and it is negative. 0.325. And then slam sine, cos, and tan of 18 on your calculators. You should get the exact same numerical values. Signs will all be positive. All right. I think that's a good little exercise on how to calculate a reference angle. Guys, don't copy this down, but what we didn't actually calculate a reference angle for an angle in the first quadrant. So what if this question, don't copy this down because I'm going to erase it, but what if I said draw and find the reference angle for, say, like 35 degrees? Well, 35 degrees is here, and what angle does 35 degrees make with the x-axis? 35 degrees. So it would kind of be a pointless exercise because the reference angle would just be 35. But we did every other case, all the other quadrants. All right. Angles can be negative too. Not in triangles, but when we think about angles in standard position, we can actually have negative angles. Does anyone have any idea how we would draw the angle minus 300 degrees? Anyone have any thoughts? What did you say there, Ryan? You go back, yeah, so 300 degrees, you rotate counterclockwise. For negative rotational angles, you start on the positive x-axis, you just go the other way. So where do we wind up, and what's the reference angle for minus 300? So I might just for this one, and you can feel free to add this or not, I'm not your dad, but if we start at 0, the bottom, and we rotate the other way, we've got negative 90, negative 180, negative 270, and all the way around would be like negative 360. So minus 300, we are somewhat here, probably closer to minus 270, something like that. Minus 300 is up in this quadrant. The reference angle is not 30. See, what some of you guys are going to do is you're going to be like, oh, 300 is closer to 270, and so my reference angle is 30 degrees. We do make a 30-degree angle with the y-axis there. However, our reference angles are always with the x-axis. We have 60 more degrees to go. The reference angle is 60 degrees here. And since we're in quadrant 1, the sine, cos, and tan of both negative 300 and 60, check it out for yourselves. They should all be exactly equal and positive. Now, while you guys are calculating, last unit for the 3U people, you guys had your special triangles, and you guys were able to, you guys can get the exact values for sine, cosine, and tan of 60. We will do some exercises later, but an expectation for you guys would be also to find the exact values of the sine, cos, and tan for any angle where the reference angle is either 30, 60, or 45 degrees, like this one. Sine 60, do I remember what sine 60 is? I think sine 60 is 0.5. Is it 0.5? No, that's totally wrong. Cosine 60 is 0.5. Which one is it? See, I need my special triangles. Cosine 60 is 0.5. Sine 60 approximately is 0.866. And they all match, because of course they do. Sines are all positive. Tan of 60. 1.732. All right, so you guys all know what makes angles related. Same reference angle. You also know what a reference angle is. We've calculated 4. Anything you guys want to chat about? Okay, a couple little exercises here. And then last unit, the 3U's investigated using the sine law for obtuse triangles. This is now the point in the course where we catch the 3M's up to speed. All right, little exercise here. So in this question, I'm thinking of an angle, or maybe angles that have a sine ratio of 0.7986. Grade 10U would be able to give me one. The one your calculator gives you between 0 and 90. A grade 11U will be able to find the other one by using your knowledge of related angles. I will help you guys with this one. So let's begin. So sine theta equals 0.7986. So what you guys will do to start off is just do the inverse sine of 0.7986. And what does it give you? It might even give you the reference angle. And if it does that, that's great. Saves us a bit of work. Shift sine 0.7986. I cooked it up to be pretty much near 53 degrees. You guys get that as well? 53 degrees. This is one angle. We have found one. One angle that has the sine ratio of 0.7986 is 53 degrees. I'm just going to add here. This is our theta r. And can you guys draw an angle of 53 degrees? It doesn't have to be perfect. Somewhere like that, 53 degrees. Now you guys should be able to determine the second angle because you guys know the cast rule and you know all about related angles. There is another angle between 0 and 360 where sine is positive as well and has the exact same decimal. I'm going to let you guys think for a second. Maybe I'll toss in a little hint here. I'll toss in my cast rule. I wonder where that second angle will be if the sine ratio for this angle is positive. I can't wait any longer. Where will our second angle be? Well, it'll have to be in the sine quadrant, right? Because that's where sine is also positive. It's going to be up here somewhere. Where exactly will it be? Well, after today, we know it must have the exact same reference angle of 53 degrees. We're basically done. What angle is 53 degrees less than 180? We just have to use our calculators and find that. I might just put like theta 2, finding the second angle here. It's just 180 minus 53. So 127 degrees. These are the two. They're between 0 and 360. Can you guys humor me? Put in sine 127. It should give you 0.7986. It's a self-checking problem. Look at us go. Sine of 127. If I could use my calculator, it would give me sine of 127. Yes. You guys did the same thing? So our calculators can give us one. The cast rule and our related angles can give us another. Let's try the next one. I wonder what our calculator would spit out for this one. Now, maybe before we begin, we're finding two angles that have this tan ratio. Which quadrants will they be in? Where are we looking for in this problem? Think about the cast rule. Where should we be looking? Which two quadrants will have a negative tangent ratio? All are positive, top right. Tan is positive, bottom left. When will tan be negative? Somewhere in this quadrant and somewhere in this quadrant. Where exactly? I don't know. Let's dive in and find out. So what does your calculator give you with this one? Our first step is just calculator. What does it give us? Does it give us a reference angle like last time? Or does it give us something a bit more funky? Who can say? Well, I could, but I'll let you guys. We're going to see. Interesting. I got negative 13 degrees. Did you guys get that too? Is negative 13 between 0 and 360? No, it's not. However, this isn't useless. This actually just tells you your reference angle. It's just negative 13, remember, is rotating clockwise. We've actually found our reference angle. What we have shown here is our reference angle is 13 degrees. That's all that told us. And now your job is simple. Which angle in the sine quadrant has a reference angle of 13? And which angle in the cosine quadrant has an angle of 13? In our first example, our calculators gave us one. We got lucky. In this one, our calculators gave us something useful. We got the reference angle from that. And now we just need to find our two values between 0 and 360. So for our first one, we're 13 less than 180. So 167. And I'll write it this way. I'll write for my second angle, we have to work for. It's 13 less than 360. So when you guys do the tan of these, it's worth checking. Doesn't take long. If you do the tan of those two values, should give you negative 0.2309. Self-checking problems. You can check to see if you're right. You guys get that? Can you guys humor me? I'm going to erase this in a second. And I think this is relevant to the back. Yes, where I stopped talking at you guys. But what if I had the same question? And what if I said find two angles where the cosine is like negative 0.1234? Do your calculators give you a negative angle or an acute angle or something different? Can you guys just do that for me? What do you get when you do inverse cosine of 0, negative 0.1234? In the first one, we got a reference angle. In the second one, we got a negative angle. What does this one spit out? Negative 0.1234. It gives you an obtuse angle, right? It actually gives you 97 degrees. So no matter which way you slice it, when you're doing these kind of problems, your calculator will give you something useful initially. Just do the inverse, cosine, sine, tan, whatever. Now, I'll let you guys do the back couple in a second. Let's wrap things up. 3M people, let's catch you guys up to speed. What happens when you use the sine law? This was a motivation problem in our last unit on a day where the 3U people learned kind of about this stuff a little bit. But what if you tried to use the sine law for this triangle here where theta is obtuse? You would do innocent, naive, grade 10U would have been like, okay, I'll use the sine law. Sine theta over 100 equals the sine of 20 over 60. And then you would calculate the sine of the angle by multiplying up to 100. And then you would get the decimal. So for the 3U people, you guys have seen this, but just follow along. We're just getting your friends up to speed. I got 0.5700. So when you guys, no matter which course you're in, when you guys were first learning the sine law, you would be just like, okay, inverse sine. And when you use your calculator, you get, I'm just going to keep this to the nearest degree. You get theta is equal to about 35 degrees. Clearly, the obtuse angle in our triangle is not 35 degrees. But now you guys know better. You guys know, well, there are two values between 0 and 360 that have a sine ratio of 0.5700. One of them is 35 degrees, but we now know that's our reference angle. To get our other angle, we just subtract from 180. 180 minus 35. The obtuse angle, did I do my math right? I think I did. 145 degrees. Yeah, in the trig unit for the 3M people, obtuse triangles are not part of the deal. However, we are now equipped to do that. The 3Us learned about that last year. All right. Very good, very good. While I pass around some practice, can you guys try those two exercises on the back? Same kind of question. Use your calculator first. That will give you something useful. And then see if you can find out the two angles that have that specific ratio. Let me just stop the recording.